Bismillah ar-Rahman ar-Rahim. We are now going to solve some examples regarding the change in entropy. One of the first example we want to see together here is this example here. Actually, this is from old exams, okay? As many times we said it, this example that we are showing you here and we are solving together are from old exams. It says we have 1 kilogram of copper. Copper is a solid. Initially at 20 degrees Celsius absorbs 5 kilojoules, kilo to the power 3, joules of heat. What is the change in entropy of the copper? When, of course, you should know that the change in entropy is equal to integral of dq reversible over t. So we have to assume in these problems that we are going to solve now, the examples, all the processes are reversible, and therefore we can use this integration and find the change in entropy for these processes. The process here is that this copper absorbs heat, 5,000 joules of heat, so its temperature is going to increase. Now remember, if a system, whatever it's a gas or it is a liquid or solid, absorbs heat, its entropy will increase because dq will be positive. If a system loses heat, dq will be negative and delta S will be negative. So in this case here, the gas has absorbed, so delta S will be positive, okay? Absorbing heat, this is solid, yeah. Solid case, eh? So the case we have a solid here. Our copper is a solid. So now, therefore here, how much is dq? Is mc dt. So we take this mass of the copper, specific heat, dt. We put this in this equation here, and we get integral of mc dt over t. So m and c are constant, so we integrate between t initial to t final. So this will be mc ln of t final over t initial, because integral of dt over t will give you the ln. So T initial is given to you here is 20 degrees Celsius, but T final, we don't know T final, so we have to find T final through another equation here. So we say that Q equal MC delta T, okay? From this equation, by integrating dQ, you can find that Q is MC delta T. So this is M is given C, that's T final that we don't know, minus T initial that we know. So T final here, we get from this equation here. So here, we have 5,000 joules of heat absorbed. So we put it positive here because it's absorbed. The mass is 1 kilogram times the specific heat of copper, which is 390. Then T final minus 20. We don't need to change here to Kelvin because it's delta T. From this equation here, you get T final. And T final in this case is 32.8 degrees Celsius. 32.8 degrees Celsius. But if you want to put the T final here in this equation, we have to put here T in Kelvin. So here, let's put the numbers now. So 1 kilogram times 390, which is a specific heat, ln of T final 32.8 in Kelvin, that's 305.8. 305.8 divided by T initial, which is 20 degrees C, that's 293 Kelvin. So here, T should be in Kelvin. Here, T doesn't have to be in Kelvin whenever you have delta T. It can be in degrees Celsius, okay? But then you have to convert this temperature into Kelvin to put it here in the formula here, because T is absolute in this case here. So you get delta S in this case, if you do the calculation correctly, you get 16.7, and the units is joules over Kelvin, okay? Joules over Kelvin, and you notice it is positive. So this is the final answer for this question here. The heat absorbed will, because the copper absorbed heat, its entropy will increase, and delta S will be positive. If, for example, it tells you that this copper has lost heat somehow, lost heat 5,000 joules or 5 kilojoules, then T final will be less than T initial, and Q will be negative, and T final will be less than T initial. If you put them in the equation here, you will get delta S negative. So this is the first example. is about change in entropy for solids. Remember that to go from 20 degrees Celsius to 32.8 degrees Celsius, the copper is still solid. It did not change phase or anything like that. Okay, thank you. Okay, let's now look at this example 2 again about the change in entropy for solids and liquids. And the problem says that we have a 20 gram of ice cube at minus 10 degrees Celsius is dropped in a lake. The lake, of course, we call it a reservoir. It's a big lake and whose temperature is 15 degrees Celsius. Calculate the change in entropy of the lake, okay, as the ice cube comes to thermal equilibrium with the lake. So the ice cube is going to melt, of course, and the final temperature of the ice cube will be 15 degrees Celsius water. So the ice will melt. It will go from minus 10 to 15, and we have to assume that temperature of the lake will not change because the ice cube is only 20 grams. So we assume that the effect on the temperature of the ice on the temperature of the lake will not be negligible. So the temperature of the lake will remain constant. Okay, it will not change. But the ice cube, its temperature will go from minus 10 to 15 because it has to come in thermal equilibrium with the lake. Okay, so it has to melt the ice. So we have to use this equation here again, and we have to concentrate on what? On is asking about the change in entropy of the lake. Okay, the lake. So delta S of the lake. Okay, equal integral of dq reversible over T, and of course the temperature of the lake is not going to change, so it will remain constant. I take it out of the integral, and this will be 1 over T integral of dq reversible, which is equal to Q over T. And this is a Q, the heat lost by the lake. It is lost to what? It is lost, it is gained by the ice, because ice is going to melt, and it is lost by, so this Q actually will be negative, okay? This Q is negative because it is heat lost. And delta S of the lake will be negative because it has lost heat, okay? So now, this Q which is lost by the lake, of course the temperature of the lake here will be 273 plus 15 degrees Celsius. This is T in Kelvin, okay? All right? So that temperature there is 288. This temperature here is 288 Kelvin. So we leave it there. Let's calculate the Q, the heat lost by the lake, and we have to go back to previous videos. So the heat lost by the lake, okay, is equal to the heat gained by the ice to go from minus 10 degrees Celsius all the way to 15 degrees Celsius. So let's calculate that heat here. Huh? Yeah. So let's calculate that heat, okay? Actually, okay? Yeah. So the heat lost by the lake will be negative, and this is positive. So we can put here absolute value to make sure that we don't get mistake in the signs, okay? Heat loss is negative, and this heat gain is positive. A negative number cannot be equal to a positive number, so we take absolute value here. But we are looking for this the positive value here, and then we put it in minus sign. So let's calculate the heat gained by the ice. Huh? Q ice, okay? The heat gained by the ice. The ice goes from minus 10 to 15, so there will be MC delta T, where it goes from minus 10 to 0 plus ML is going to melt at ML, ML for melting the ice at 0 degrees Celsius, plus another MC delta T, it will take it from 0 to 15 degrees Celsius. But let's put the numbers now here and calculate this. So this will be, the mass of ice is 0.02 kilogram times specific heat of ice is given to you is 220 times delta T here, it will be 0 minus 10, which is equal to 10. Remember, T final here is 0, and T initial is minus 10. So final, which is 0 minus 10, will give you 10 here, plus another 0.02 times 3 times the power 3, that's L fusion of the ice, okay? Then you add to this another MC delta T here, which is 0.02 times 4190, that's specific heat of water, times change in temperature. We are going from where to where now? We are going here from 0 to 15, which is 15 degrees Celsius. If you do the calculation for this QIs, you find, if you do it correctly, then you find a minus 8,361 joules. That's the heat gained by the ice. And the heat lost by the water, by the lake, Q of the lake, will be exactly minus 8,361 joules. Okay? We assume that the lake and the ice are in an isolated system. Okay? So heat gained by the ice equal heat lost by the lake. So let's take this value here and plug it here. I told you it's negative to find delta S of the lake. So delta S of the lake in this case will be minus 8,361 joules, okay, divided by a temperature 288. So if you do correctly these calculations, you get minus 29 joules per Kelvin. You notice that delta S is negative, and don't be alarmed by this, because of course if a system loses heat, like the lake is losing heat to melt the ice, delta S will be negative. Okay, so that's the problem is complete now. He's asking about the change in entropy of the lake. So delta S of the lake is given here. Now let's go one step further and calculate the change in entropy of the ice, and then ask about the change of the entropy of the system. Now if the change in entropy of the system is negative, then I'm in trouble. Okay, so delta S of the entropy change of the system would be positive because it is irreversible process, and we said for irreversible processes the change in entropy should be positive, okay, or 0. Now let's calculate. Let's go one step further. Now the problem is finished. Let's calculate delta S for the ice. So delta S for the ice. Of course, the ice is going to go through 3 steps. You remember, it will gain heat, and temperature and phase is constant. It will change phase, and it will gain heat again. So I'm going to use dq over t again, but I have 3 steps here. So I have to go from minus 10 degrees Celsius to 0 degrees Celsius. Of course, MC, it will be MC dt over t, okay, plus then there will be a melting, it will be ML fusion over T of a fusion, which is equal to 0 degrees Celsius. Be careful, you have to change this into Kelvin later, plus integral from 0 degrees Celsius to 15 degrees Celsius, where you have another, again, MC dt over T, okay? So there will be 3 terms here for delta S of the ice. So if you do the calculation correctly, there will be MC ln of T final over T initial for this case, plus M L of fusion over T of fusion, which is 273 for ice, plus another M C ln of T final over T initial. Be careful here, T final and T initial are different from here, okay? If you want to do the calculations now, you can calculate this and get delta S, which is 0.02 times, this is ice, 0, ln of what? Ln of T final, which is 0 degrees Celsius, which is 273 Kelvin, divided by 263 Kelvin, okay? That's T initial, plus 0.02, which is the mass of ice, times L fusion, 3 10 to the power 3, divided by 273, plus another term here, 0.02 times specific of water, 190, ln of T final, which is 15 degrees Celsius, which is 288, divided by 273, which is the 0 degrees Celsius, okay? If you do the calculations correctly again here, you will find a value of 30.5 joules per Kelvin, and it is positive, okay? You notice that this is positive. Why is that? Why is it positive delta S? Because the ice has gained heat. Why is it negative delta S? Because the lake has lost heat. Remember these 2 concepts, okay? Now, if you want delta S of the system, it should be positive, Okay, delta S of the system will be delta S of the lake plus delta S of the ice, and it will be minus 29 plus 30.5, which is equal to 1.5 joules per Kelvin with a plus sign. And this is the final result. In case you are asked to find delta S of the system, you have to find the delta S for the lake and delta S for the ice here, okay, and then add the two numbers algebraically to find delta S of the system. System, which means ice lake system. Okay, remember that the specific heat of ice and specific heat of water are not the same, so it's better here to label this as specific heat of ice, because here the phase is ice, still not melted, is ice. So it's sea ice here and sea water here, okay? Because here the melting process happened here, so now the ice became water, so you have to have a specific heat of water, and it's clear here. You can see that that's the specific heat of ice, and this is the specific heat of water. Similarly here, you write sea ice here and sea water, because here the phase is ice and here the phase is water. So sea ice here, as you can see it here, 2220, and sea water here, you can see it here is 4190. Okay. Now the other thing is delta S of the system is positive. Of course, this is an irreversible process. No way that the water, the 20 grams of water, will spontaneously become ice again just by itself. Okay. This is irreversible process. It's a one-way process. When you put ice in the lake, water, or in the lake, it will melt. Spontaneous melt, and delta S will be positive, and in accordance with the second law of thermodynamics, delta S for irreversible process should be positive. Thank you.